Hello everyone. Today I wanted to record a video on nuclear fusion and nuclear fission. These are two very interesting topics which are related to the breaking and combination of the nucleus. In case of nuclear fusion, you can relate it with any common word which you use in your daily life. For example, fusion of two different musics or fusion of the food as well. So nuclear fusion happens when there are two light nuclei, for example hydrogen and the hydrogen, and they are combining with each other. So this process is called as nuclear fusion. Nuclear fission happens just opposite of the fusion. In case of nuclear fission, there is a heavy nucleus, for example, uranium, plutonium, thorium. Now, this heavy nucleus splits into two or more parts. So, this is called as fission. And the part which is coming out, it may be a smaller part of uranium. Further on, the reaction will go on, and you will get this material converted into something like krypton or barium, and this one also, right? But this happens much later. But in between, lot of energy is created. This energy which is coming out is called as nuclear energy. Nuclear energy. Now, the thing is, you may be having a question, why do nuclei fuse, or a heavy nucleus breaks, right? So this is a very good question, and to understand that, you can use the graph of binding energy with the nucleon number. So if you see the binding energy graph, and let me draw it first. So here on the x-axis, I'm drawing the atomic number. So instead of saying atomic number, just let me correct myself. I'm saying here the mass number. So it's not atomic number, it's a mass number graph. Mass number on x-axis, which is A, and binding energy per nucleon, or binding energy divided by the mass number graph on y-axis. So when you draw a graph and general graph, you will get a pattern something like this. Now this graph is not clear, and let me put some numbers here. So let's say this is 20, 40, 60, 80, etc. Right? 100, and it can go on and on up to the last element. Here, this is the binding energy per nucleon on y-axis, and we will get back the maximum binding energy somewhere here. Now, which is this element which is having the highest binding energy? And in this peak, there are two elements which are most probably found, and one is either iron, or the another one nickel. These are the two elements which are sitting on the peak of this curve, and they are having the highest binding energy. Highest binding energy. Let me change the color so that it looks beautiful. Even when I'm highlighting, this peaks something like this. You can see from the graph the lighter nuclei in this region, okay, with less mass number, and here high mass number. They both have low binding energy. So you can see the light nuclei, and the very heavy nuclei have low binding energy. Low binding energy per nucleon. Low binding energy per nucleon. So what is problem? The problem is everyone wants to be rich. Even in our society, we want to attain high stability range. Right? We want to earn more money. We want to have a good car. We want to have a very beautiful home, big home, so that we are more stable away from the problems. Same thing happens with these very high mass number nuclei and low mass number nuclei. They want to achieve this stability. So the low mass number nuclei which are here, they have one option. They can join the other low mass number nuclei so that they can shift towards the peak. Now, the problem with the high mass number nuclei, they are very heavy and unstable, right? So, they want to split themselves so that they can achieve stability. So, one portion goes here, one portion goes here, and this process is called as fission. Now, let me show you with the help of a reaction. When you break one uh, big nucleus, which is let's say 92 uranium 235, 92 uranium 235, or you can say 92 uranium 230, let's say 92 uranium 235. Now this 92 uranium 235 will take one neutron. When this neutron hits this 92 uranium 235, it becomes even more unstable. It's already unstable, now it's becoming more unstable. And when it becomes more unstable, first of all, let me complete the reaction. What it will look like. Now it will look like 92 uranium 236. Now 92 uranium 236 will break into two lighter nuclei. One is barium with the atomic number of 36 and atomic mass number of 89, plus another one is krypton with atomic number of 56 and the atomic mass number of 144. Now this reaction is incomplete, not complete yet. So what happens? There are three neutrons which came out from the nucleus. They are also added in this reaction. Now this reaction is complete, and this is the reaction of nuclear fission, right? So you can see when 92 uranium 235 gets one neutron, it breaks into a barium plus one krypton. Breaks into a barium and krypton, right? So heavy thing broke into two smaller part, barium and krypton, Now it's more stable, and you can see from their mass number, they this mass number is reaching near to somewhere that plateau, though it's not perfectly there, but it's near to that plateau, right? So compared to 236, 89 and 144 will have more stability. Now, the question was, why is there nuclear fusion? So, nuclear fusion happens also for the same reason. And if you see the graph, so at the bottom of the graph, somewhere here or here is the hydrogen. And hydrogen is a single nucleon element, and it feels quite lonely, I think. That's why it's very much interested in fusion, right? Inside of all the stars, or almost all the stars, I can say, almost all the stars, nuclear fusion is taking place. Nuclear fusion is taking place, right? And in their core is hydrogen. Hydrogen is the element which is fusing in their core. So let me show you what type of reaction goes on in a star. Let me change the color. So let's say there is one hydrogen. It combines with another hydrogen. You can say this is proton as well, because inside the nucleus there is no neutron. So you can say this is simply a proton. Yeah, no need to say hydrogen if you don't want to. So this is the proton. One proton combines with another proton, and what will be formed in this process? A deuterium. So deuterium, you may be aware of, it's an isotope of hydrogen which is having one proton and one neutron in its nucleus, right? So deuterium is formed. But the thing is, there was some extra charge when we were seeing this reaction at the left side. And what is that extra charge? One proton here, one proton here. And right side, we are seeing only one proton. So two proton left side, two proton left side, one proton right side. So where is that one extra charge which was left side gone? So that extra charge comes out in the form of beta plus decay. But beta plus decay never happens alone, or it may happen alone, rather, you can say, but it is accompanied by a mysterious particle which is called as neutrino, right? And neutrinos come in two categories. One is antineutrino and another one is a neutrino. So here in this case a neutrino will come out in case of beta plus decay. Beta minus decay is accompanied by anti-neutrino. Now this reaction won't stop here. So one deuterium further combines with one more hydrogen, right? So 1H1, 1H2 plus 1H1, they combine together, and what they form? They form 2He3. Now this is a isotope of helium, right? So light isotope of helium, right? But this helium isotope which is formed at right side is not alone. It's accompanied by a gamma ray, which is a burst of energy. We can stop this nuclear fusion reaction here, but let me explain you how helium is formed within the core of the star. So now we have come to this process from 1H1, to 2He3. Same reaction goes on with the another hydrogen group, and we come to the same reaction, which is 1H2 plus 1H1 gives you 2He3 plus a burst of gamma rays. Now what we have? We have at the end, let me change the color, we have at the end two helium isotopes. One is here 2He3 and another one is 2He3. They are present in the core of the star. Now they are very much ready to take part in the reaction. So here 2He3 plus 2He3, they combine together, and what they do, they form 2He4 plus 1H1 plus 1H1. 2He3 plus 2He3. So here helium is formed, which you see in the periodic table, 2He4, right? So helium nucleus is formed, and one hydrogen is released here and the another one is released here, right? So what you can see here, a very interesting thing you can see here. Though in this whole reaction, if you start from here, one hydrogen, 2 plus one more hydrogen, 3. So 3 hydrogen took part to form a helium isotope, right? To form a helium isotope. Now 3 hydrogens, they took part again to form another helium isotope, and these two helium isotopes here, these two helium isotopes, they took part to form the another stable helium isotope, right, which is 2He4. But so total 3 for this reaction, 3 for this reaction. Total how many hydrogens took part in the reaction? 6 hydrogens took part in the beginning of reaction. But if you see the final reaction, what happened here? Here, along with the helium isotope, 2 hydrogens were released. What? 2 hydrogens were released. So 6 hydrogens, they formed 2He4 plus gave away 1 hydrogen plus 1 hydrogen. So overall, lot of energy was generated, but only 4 hydrogens were converted in the end, because 2 were returned back. Okay? So this small returning back to the nucleus or into the core of the star helps the reaction to go on for very long time, because all the hydrogens which are taking part, they are not getting consumed instantaneously. Some of them are returned back. So we should learn a lot from the reaction and from the stars as well, that as a human we should not utilize all the resource which is available on the earth. Rather, we should give something back in a very positive way to our environment, to our society. In that way, we will sustain for a very long time on this earth. And we mean here the human race, the animals, the creatures, everything. Everyone has a right to live on this earth, right? the birds, the trees, the plants, we all are interdependent on each other, and we should make our earth more green, more beautiful, and more livable. Thank you. Please subscribe to my channel and uh, keep following for more videos like this. See you.